Bismillahirrahmanirrahim. Assalamu alaikum and welcome to this session. Up till now in our study of queuing theory and queuing models, we've only focused on service centers in which we have a single queue that is feeding into either a single server or multiple servers. But simply restricting ourselves to the study of only such systems will not allow us to model computer networks, because in computer networks we have various routers and various networking devices connected together. So if we want to model this as queuing systems, we would have to consider the case where the output of one queue may be the input of another queue. It may be that the output of multiple queues is aggregated together and then it forms the input of another queue, or the output of a queue is probabilistically routed to some other queue. So there are many different problems that we have to analyze if we have to model a computer network. Essentially, the study of a network of queues is the field of queuing networks, which we're going to talk about today. So first of all, let us recap the things we've studied. So a queuing system is a system in which we have a queue. There are certain arrivals coming in. If the server is available, the customer goes straight to the server to get the service. But if the server or the servers are not available, then the customer has to queue for service. So this is the basic idea of a queuing system, and we can differentiate different queuing systems we've studied into mainly two types. The first type is what we would refer to as queuing centers, in which when the customers arrive, they would in general also queue for service if the customer is busy servicing other customers. We can also subdivide this class into two kinds. One kind would be a fixed capacity service center, in which the service capacity or the service rate of the service center does not depend on the load being applied. An example of this would be the MM1 queue. Regardless of how many customers we have in the system, the service rate would still be the same. But you can also have the case of load-dependent service centers, the example of MMC servers, where if we apply more load, typically the service rate of the service center would increase up till a certain threshold. So we can see both these examples shown on the screen. Another basic kind of a service center is what is known as a delay center. And in this we have basically infinite servers. So every customer that comes in is serviced immediately. So in this we don't have any queuing and we don't have the dependence on the load. Every time we come in, we are just going to face the service time, and the service time can be described by a distribution with some known average. And this average does not depend on the load. So delay center is often used in the modeling of computer systems and of computer networks to model the human behavior. For example, if we want to model a computer system in which we have terminals which are being operated by humans who happen to think on their terminals and then type commands, this can be modeled as a delay center with some known thinking time. So we'd be seeing more of this as we proceed in this lecture, but for now we note that there are two kinds of service centers, queuing center and delay center. Before I go on to develop this session further, let me outline what we're going to cover today. Initially, I'm going to talk about what queuing networks are. I'm going to introduce the notion of a queuing network, and then I'm going to talk about the queuing networks that we can solve. We would see that there are some queuing networks that we can analytically solve, and there are many networks that we cannot solve. So we can only solve for queuing networks in which we have some nice properties. And we would formalize this notion of having nice properties by noting that some kinds of queuing networks have a very convenient solution, where by solution basically I mean that if we have a certain number of jobs in a queuing network, what is the distribution of jobs in the network. How many jobs would be in Q1, how many jobs in Q2, and so on. We would see that if our network is well behaved, then they have a product form solution in which we can analyze every queuing system separately, and that is very convenient for us. But if we have to analyze the whole system jointly and we don't have the desirable property where we can separate the network into individual queues that can be analyzed separately, we can actually give very little results analytically. Lastly, in the second part of this session, I'm going to talk about queuing theory and particularly queuing network theory as applied to data networks. So we start with queuing networks. Let me show you a queuing network and we'll see what are the challenges that arise in a queuing network. So we see on this slide that there are 5 queuing nodes, where every node represents a service center, like the service center we've seen. It may be a queuing center, it may be a delay center, it may be modeling an MM1 queue or a MMC queue, or indeed a delay center. But they can be arbitrarily connected. It can be that the traffic is being partitioned as it moves out of a queue, and probabilistically it is being routed to other downstream queues. So the output of one queue becomes the input of another queue. So the output of the first queue itself is random, and then it goes into the second queue, and if we have to analyze it, we have to take into account both these queues. So then the other problem is of merging of traffic. It can be that the output of multiple queues are being merged together and they go into another queue as the input of that queue. Furthermore, we have the issue of tandem queuing. We can imagine this in a real life scenario where we go into a supermarket. Firstly, we go to a salesperson. That salesperson gives us a chit which we'll have to take to the cashier. So we get service at different service centers, and this service takes place in a certain sequence. So this then can be modeled as a tandem queue. So in a queuing network, if many multiple queuing systems are connected together, we have to take care of all these issues, and we will see that unless our network has the special property that characterize those networks that have special property known as a product form solution, we can basically do very little analytically. So essentially all our interest then is focusing on this class of queuing network that we can analyze. And most of the research in this area is on expanding this area. So earlier we knew that some particular class of queuing networks are product form, and from then on it has been a continuous effort of generalizing beyond that particular class, and we're going to see this in more detail very shortly. So like for the queuing centers, the service centers, we had a notation for classifying the different queues, and that notation was the Kendall's notation. For queuing networks, we can classify them into 2 or 3 different ways. The first way we can classify queuing networks is according to the fact if the requests are coming in, if those requests are constant over time or not, and in particular if the arrivals are coming from outside the queuing network. If you have such a system in which the arrivals are coming from outside the queuing network, they take service from the queuing network and then they depart from the queuing network, we have what is known as an open queuing network. On the other hand, if we have a queuing network in which we have a fixed number of jobs and they continuously loop around amongst the various devices, then we have a closed queuing network. In an open queuing network, such a network is characterized by the arrival rate, because that is what is coming from outside the queuing network, and typically we assume that everything that is coming in is eventually output. So the throughput we typically assume is equal to the input or the arrival rate. For the case of closed queuing network, we assume that there are fixed number of jobs, and therefore we have to specify these number of jobs. We typically use the notation of n to represent the number of jobs in a closed queuing network. Let me now take a brief interlude where I introduce the use of queuing networks, especially the use of open and closed queuing networks in the modeling of computer systems. And in fact, it has been one major success story of analytical modeling, that we've been able to model very complex computer systems that are multi-resource. We not only have a single queuing system, we have multiple queuing systems that interact in very complex ways. We have the CPU, we have the memory, we have the disk, and we also have the network interface. So all of these are talking to each other, and it is challenging to model a computer system, not leave alone a computer network. It's a challenge to model a computer system. The first attempt in this regard was the attempt by Alan Scherr, who modeled the CTSS computer at MIT in 1965, borrowing a queuing network model that is used in operation research. It's a very simple model. It's a degenerate example of a queuing network. We don't have multiple service centers. We have a single system, and we have a queue before it, and everything that is output goes back into a delay center. So we call this machine repairman model because we can assume that there are some fixed number of machines that we have, and we want to have them operating. But sooner or later these machines would break down, and every time the machine breaks down, this counts as an arrival to the machine repairman. So this is modeled as you have fixed number of jobs in the system, and every time a machine breaks down, this is actually an arrival to the machine repairman system. And if you have multiple machines come into the machine repairman, assuming that there is just a single machine repairman, then you would have to queue. Assuming that you have multiple machine repairmen, then if there are more number of machines coming in, then you have the number of repairmen, then they would have to be queued. So it's a very simple example. It's a very simple model, and we can specify it using the average breakdown time and the average service time, and with just 2 or 3 explicit parameters showed that he could actually model very accurately MIT's CTSS system, which is a complex system. It was not multi-programmed, but still it had many different complexities that this model did not explicitly take into account. And this was in fact the beginning of the golden era of analytical modeling of computer systems. And this created an entire field. And we would see that this actually also opened a paradox. And that paradox was, we're using a very, very simple model to represent a very complex system. Yet the output seems to be very good, while many of the assumptions are not being met. So this paradox, I would just skip over it, and I'll come back to it when we talk of operational analysis in the coming lectures, when we talk about the role of the assumptions that we make in analyzing the different systems. We see that it is often the case that we make very strict assumptions, but those strict assumptions are not necessarily true. In this case, it was actually shown that it is not necessary for the system to have an exponential distribution for this system to be solvable. In other words, this model has a product form solution even when the system does not have an exponential service distribution. And that is when we cover the class of BCMP networks, we would see that initially we had very simple models of product form solutions, and then we have been continuously expanding and generalizing from this subset of models that we assumed earlier to have product form solutions. So machine repairman model was an early model and used by Alan Scherr, and it was stepping stone for the use of analytical modeling in the field of computer systems. This was followed by the introduction of the central server model by Jeff Busen, who used it to model a multi-programmed computer system. In a multi-programmed computer system, you have multiple programs using the computing resources. And we cannot use a simple model like machine repairman model to model the complexity that we have in a multi-programmed system. In particular, we have a central server here, and it is assumed that arrivals come to the central server and then they are dispatched to the disk or whatever device it has to go to, and then it comes back to the CPU, and eventually it will complete and go back. And you may have a central server model which is closed, and you can also have a central server model which is an open network, in which external jobs are coming. They come to the server, they are dispatched to the subsystem for further processing, then it comes back to the CPU, and it may go out of the system. If the arrivals are coming from outside the system and going out of the network after processing in the queuing network, we refer to this network as an open network. In a closed network, the number of jobs remain the same. Okay, another kind of classification that we can make of queuing networks is according to the workload that is subjected to these queuing networks. So in a queuing network, we can have a transaction workload. A transaction workload, the reason for naming it transaction workload is mainly historical. It was used to model ATM networks, banks, travel agents, on which external request came, and then after being serviced, maybe for service it went to the database server or some other server or some other device in your queuing network. Eventually, after taking service in your queuing network, it departed. So then this is an example of a workload that is applicable to an open network. You can also have other workloads that are applicable to closed networks. In particular, we have the batch workload and the terminal workload. In a batch workload and in a terminal workload, we assume that we have a constant number of jobs. In addition, in terminal workloads, we also assume that there are terminals on which we can model humans operating these terminals, and they are thinking on these terminals. So these humans either are in the thinking mode or they are in the waiting mode. So they may be thinking of what commands to give, and after giving those commands, they are waiting for the execution of those commands. So we can classify workloads in three basic types, and for open networks, we make use of transaction workloads, and for closed networks, we make use of batch and terminal workloads. Batch workloads are like the batch processing in computer systems, in which you have a set of commands that are being run one after the other. We assume that in a batch workload, the number of jobs are constant. So you continuously have some job which will take place, the place vacated by a completing job. So the summary of this then is that batch workloads and terminal workloads apply to closed queuing networks, whereas transaction workloads apply to open queuing networks. After classifying the kinds of queuing networks, we can now proceed to the question of solving these queuing networks, where solving these queuing networks essentially means we want to know the joint probability distribution of how the jobs are distributed all over the network. In particular, we may be interested in calculating the joint probability expressed by the function shown on the screen. We are interested in calculating the probability of n1 jobs at the first queue, n2 jobs at the second queue, n3 jobs at the third queue, and nm jobs at the mth queue. So if we want to analyze this, it becomes very difficult for us to handle everything at the same time. It is only easy if we have a separable queuing network to analyze queuing networks. So first of all, let me show you how things can become difficult. For that, we would be seeing the state space of a queuing network, a very simple queuing network. So in this slide, you can see a queuing network in which we have two servers connected in a tandem fashion, and the output of the second server is being fed back to the first server. So this then is a queuing network, and we need to characterize this by defining how many jobs we have in this network. So we take the example of just 3 jobs just to analyze what is the complexity of solving such a queuing network in state space by outlining what the different states would be. So if we only have 3 jobs and 2 service centers, then we have all these different states that we can have. We can have 3 jobs at the first center and none at the second. We can have 2 jobs at the first center and 1 at the other. We can have 1 job at the first center and 2 at the other, or we can have all the jobs at the second center. So this then looks manageable, but imagine that if you have 5 service centers, imagine that you have 10 service centers, imagine that you have 100 service centers, and you have 50 number of jobs. You can imagine the number of state would increase very, very much. And therefore, it is in fact the case that state space solution of queuing networks is non-trivial. It is intractable except for very small queuing networks. In principle, we can always outline the different states that we have, and using standard continuous time Markov chain techniques in which we create balance equations and then solve for them, we can solve this. But if the number of states are too much, then we cannot do a lot about such a network. We need more efficient methods, and efficient methods only exist if we have the property where every service center can be treated in isolation. Currently, we can only solve for such queuing networks. These are known as the separable queuing networks, also known as product form queuing networks. As an example of a separable queuing network, let's consider a very simple example. We have a tandem queue. The arrivals are coming to the first queue, and the departures from this queue are being fed to another queue. And the service rate of each one of these queues is given to be identically 10. And we know that the arrival rate, external arrival rates, are only coming to the first queue. So lambda is being fed to the first queue. The input to the second queue is the output of the first queue. Let us now analyze these queues. It turns out that the marginal distribution, which is simply the probability of having some number of jobs at that particular queue, is identical for both these queues that are working in tandem operation. How can that be? For that to be true, it has to be the case that the output of the first queue is statistically identical to the input of the first queue. In only that case would the input of the second queue be the same as the input of the first queue, and they would have similar results. In fact, that is the case. If we have Poisson arrivals to the first queue, and the first queue has exponential service distribution, then the departure process would also be Poisson with the same rate. And that actually indicates that the second queue would have arrivals that are also Poisson with the same rate as it was for the first queue. So in that sense, both these queues are identical. And there is an additional property that is very important, and that follows from this combination of Poisson arrivals and exponential service distribution, that the departures are independent from the number of customers in the queue. That actually allows us to separate this tandem queue into basically isolated service centers. We can analyze them separately, and then the joint distribution is just the product of the individual marginal distributions. So that is the beauty of Poisson processes and the beauty of product form queuing networks, that we can decompose a complex looking network into simple isolated service centers that we can analyze on their own, and then the overall solution is just the product of individual solutions. The queuing networks that have joint distribution of this form are known as product form queuing networks. To understand them, let us just revise some important properties of Poisson processes. The first important property is that if we aggregate multiple Poisson processes, then the aggregate process is also Poisson, and the rate of the aggregated process is just the sum of the rates of the constituent Poisson processes. In fact, the reverse operation also holds. If we have a Poisson process and if we want to decompose it into multiple Poisson streams, then we can in fact do that while still retaining the Poisson nature of the departure processes. So this is a very fundamental result, and this has to be complemented by a very important result which is known as the Burke's theorem, and that is fundamental to why we can actually have product form queuing networks. So to understand Burke's theorem, let us analyze the queue that you can see on the slide now. You see that there is a server that is exponentially distributed, and it has an arrival rate that is Poisson with rate lambda. We see that according to Burke's theorem, the departure from this queue would also be Poisson. It has the same rate. This is a very fundamental point, that the arrival rate is the same as the departure rate, and the departure process is a Poisson process as well. In fact, if you look this up in advanced books of queuing theory, you would see that such a system is actually time reversible. We can make the departure as the arrival, and still the system would behave in the same manner. For our purpose, the important point is that the departure rate is the same as the arrival rate, and also that the departure process is independent from the number of customers in the queue in the first service center. This is fundamental because it allows us not only to say that the arrival to the second queue is also lambda, but also to say that this arrival is independent from whatever there was in the first queue, and therefore these are independent queues. So this is a very important result that leads to the product form solution, that the joint distribution is just the product of marginal distributions, because each one of these queues are independent of each other, and they retain the Poisson nature of arrivals because they have exponential service distribution. As long as the service rate is more than the arrival rate, all of the arrivals are going to be processed to the output. Okay, let us now further study some simple queuing networks to then generalize them to the case where we have queuing networks that we can analytically analyze, so that we can also know where the boundaries are. So up till now we've only focused on a simple example of a tandem queue. Let's generalize this tandem queue so that we allow arrivals at any arbitrary queue, but we only place the restriction that the departure of a queue should not go to a queue from which this job has already had service. So there is then no feedback in the network. Such a network is known as a journal feed forward network. So you can have arbitrary connections and you can have arrivals at different queues, but you're assuming Poisson arrivals and exponential service distributions, and you're also assuming that there is no feedback. It turns out that if you have feedback in the network, then it can destroy the Poisson nature of the input. As an example, let's see the illustration on the slide. We can see a queue, the arrival of which is lambda, and the service rate is more than lambda, so there is no problem there. The output of this would be lambda, but the problem that we have is that some part of the output is actually fed back into the input, and assuming that only epsilon amount of traffic is going out, which is very small, and most of the traffic is being fed in, Then for every exogenous arrival, which is every external arrival, you have many jobs that are fed back to the input queue. And because of that, for one external arrival, you have a whole burst of fed back jobs, which breaks the Poisson nature of the arrival. So it looks like we've reached the limit of the networks that we can solve. However, luckily, the introduction of this feedback does not really affect the product form queuing network solution. It was shown firstly by James Jackson in 1957 that even if we have this feedback element, still the product form solution would still apply. Obviously, there are some restrictions, and I would now outline those restrictions. But before I do that, I want to highlight that this is a very fundamental result. And this created a lot of research. And as I would mention in the end of this session, that this was in fact the work which brought queuing theory into the study of computer networks. So the restrictions are that all nodes must have exponential service time distributions. They must also be servicing the incoming arrivals in a manner which is first come, first served. Also, the arrivals that you have externally from outside the network must be Poisson. You may have feedback, but the external arrivals must be Poisson. Lastly, you can have routing where the output of one queue is not deterministically going to some other queue. It may be going probabilistically to some queue, but this routing is Markovian, and also it is fixed probability. So if we have these restrictions, Jackson showed that fortunately networks that have feedback, if they fulfill these conditions, still have a product form solution, which is very good for us. The thing is that the network, it seems like it forgets that it has feedback. It simply takes the aggregate input, where the aggregate input is the external arrival plus the arrivals from other queuing systems. And it basically calculates a rate from that. And then, as before, every queue can be analyzed independently. So as an illustration of this, let's do an example to make things more concrete. Imagine that you are part of a company, and that company has a 3-node telephone system. So basically you have 3 service centers. The first service center is represented by the number 800, and people call into this number, and the arrival rate of coming to this number is 35 per hour. And then typically they listen to the instructions, they decide and push a button. It takes a mean of 30 seconds, and then they are routed to either the policy section or the claims section, and you have a service facility for each of these sections. For the claims section, 55% of the calls are going there, and the claims section has 3 exponential servers with mean service time of 6 minutes. The remaining 45% go to policy service that have 7 servers with exponential service times of mean 20 minutes. The interesting part is that you can have feedback. In this example, there is some feedback. 2% of the claims people would go to policy service, and 1% of the policy people would go to claims service before they actually go out of the system. We want to solve this system and calculate the average queue size in front of each node and the total average time a customer spends in the system. This thing is also known as the sojourn time. Let us now, first of all, graphically plot the information that we have. So we see that the external arrivals are at a rate of 35. So we represent gamma, which is representing the external arrivals as 35. The service rate of the 800 number is 120. Of policy as mu is equal to 3. The mu for claims is equal to 10. We also note that you do not have the same number of servers at different places. For policy, you have 7 number of servers. For claims, you have 3 numbers of servers. So this then is an arbitrary network of MMC servers. Okay, so from the arrivals, where do we go? We go in a probabilistic fashion. 45% would go to policy and the remaining would go to claims. And from claims, 0.02 probability, or basically 2% people would go to policy, and from policy to claims, 1% people would come. And the remaining would go outside the network, and that is shown by the external departures of the jobs. So how do we analyze this? To analyze this, we have to determine the aggregate arrivals at every queue. So for the first queue, which is the 800 number queue, the arrivals are just the external arrivals. So for that, lambda is equal to simply 35. The interesting part is to calculate the lambda for policy and the lambda for claims. One thing is pretty straightforward. 45% of the incoming 35 customers that are arriving per unit time are being fed to policy, and the remaining 55% would go to claims. But there is also a feedback element. Some policy customers are going to claims and some claims are going to policy. So we can actually write down linear equations and then we can solve for these, and the solution is shown on the left bottom side of this slide. You see that lambda claims is calculated to be 19.4 and lambda policy is calculated to be 16.1. For 800 number, we know that the arrivals is equal to 35. So essentially we have all the information we require now. We have the arrivals, we have the service time distributions. We also know that 800 number is an MM1 server. The policy server can be imagined to be an MM7 server. Regardless of the fact that there is some feedback, we can analyze it as if it has Poisson input. And also claims can be analyzed as an MM3 server. Let's now solve this and see the answers that we get. So for the 800 number server, we see that we are analyzing it as an MM1 server. We know lambda, we know mu. From that we can calculate rho, and from that we can calculate all the other performance measures, the number of customers in the queue, the average wait time, and so on. Similarly, using the formulas for MM3 and MM7, the formula for MMC that we studied, we can determine performance metrics for those particular queues in isolation. Now the interesting thing is, from this we can calculate the marginal probabilities, and the joint distribution is just the product of these marginal distributions. And that is the power of the result that was proved by Jackson. Okay, so up till now, we have only been focusing on open queuing networks. So tandem queuing, the result that we had from Burke, the Jacksonian network is also just limited to open queuing networks of the form that we saw up till now. We see that even Jackson's network can be generalized to the case where we have a closed queuing network. The problem is that straight away the results cannot be just ported to a closed queuing network, because for the open queuing network we were assuming that we were actually having independent queues. So if you have independent queues, the result holds. But if you have a closed network, then you have a fixed number of jobs. So if there is a job in some queue, that job cannot be in some other queue at the same time. And because of that, you have dependence amongst the different queues. It turns out, as was shown by Gordon and Newell in 1967 and earlier by Jackson in 1963, that even for a closed queuing network, we can have a product form solution. We cannot determine the joint probability distribution uniquely, but multiplied by some multiplicative constant. And so therefore we have to normalize it. And this normalizing constant, g of n, is actually a function of the number of jobs in the system. It turns out that this is really non-trivial to calculate. And in fact, much of the research in the solution of closed queuing networks has been in devising efficient ways of calculating this normalizing constant. One known method is the method proposed by Jeff Busen, which is known as the convolution method, which we will not be covering in this course. We will in fact cover an approach which is known as the mean value analysis, in which we sidetrack this step completely. We do not calculate this normalizing constant. The price we have to pay for this is that we cannot know the exact distribution. We can only calculate the mean values. So that would be covered in a future lecture. Let us just draw the landscape of product form queuing networks. We saw that Jackson networks are product form. We saw that Gordon-Newell networks are product form. Can we generalize further from these networks? The thing is that we have some restrictions when we are limited only to Jackson and Gordon and Newell kind of networks. The restrictions are that we only can have exponential service. We can only have FCFS service, and we are limiting ourselves to a single job class. It turns out, as was shown by Basket, Chandy, Muntz, and Palacios in 1975, that there is a broader class of networks that have product form. We do not actually need to have this restriction of exponential service and of FCFS and of single job class. In fact, we can do away with all these restrictions. We can have several job classes. We can have many queuing scheduling disciplines and also many distributions of service times, but obviously it is restricted to some conditions that we must satisfy. And these conditions are listed now, and we call such networks BCMP networks because of the names of the people who proposed this network. The main results are that we are not limited to just FCFS service centers, but we can in fact have other scheduling disciplines like processor sharing and infinite servers and last come first served preemptive resume. And of these four, for the processor sharing and infinite servers, multiple jobs are in service at the same time. We can also have multiple job classes. Up till now, we've only focused on the case where we could deal only with a single job class. But now we can have different jobs belonging to different classes. And we also have generalized the need of service time distribution to be exponential. Now it can be some arbitrary distribution if the server discipline is not FCFS. If we have FCFS discipline, then it is necessary that we have exponential service. But if we have some other discipline, then we can have other service distributions. This, by the way, is the reason the modeling of the CTSS computer system at MIT by Alan Scher was so well modeled and gave so accurate results, because the assumption of having exponential service and of FCFS discipline was actually not needed. In fact, the scheduling discipline of that computer system was in a sense round robin, which is like the processor sharing discipline that we have. And when you have that, the service distribution does not matter as long as you have a rational Laplace transform. So I refer you to the textbook for more details on the BCMP networks. We can now proceed to how the queuing theory models and the queuing network models have been brought into the world of computer networking. So the credit of this goes to Leonard Kleinrock, and it was his PhD work in the late 1950s and the early 1960s which really laid the foundation of the analytical modeling of computer networks. And the first page of his PhD proposal, a snapshot, is given on the screen, and you see that it was in 1961 when he started analyzing computer networks in analytical ways. He used the method of queuing theory, and this was way before the internet came around. In fact, the first packet on the internet was only exchanged in 1969, which was, by the way, in Kleinrock's lab. But still, he had a theory ready for analyzing computer networks even before ARPANET was conceived. It was maybe 8 or 9 years before that. So the problem he tackled was, how can we model computer networks that are very large? He basically borrowed the theory from the theory of waiting lines. He used queuing theory to model these resources, because networking nodes are also dynamic resource sharing nodes, and you would have queues forming up when you have multiple packets come in and all of them cannot be processed at the same time. And much of the queuing theory also analyzes the same metrics we are interested in. We are interested in the average delay, in the average throughput, and similar performance metrics. And so Kleinrock discovered that queuing theory is a very good match for the data networks that he wants to study. But the problem was, in a data network, all the devices are connected together. Most of the work in queuing theory was focused only on single service facilities. We were not thinking about how the different queues can be connected together, with the singular exception of the work of Jackson, who had analyzed network of queues in 1957. So it was around about 61 when he submitted his PhD proposal, and at that time he looked up Jackson model and wanted to implement it for computer networks, but his analysis of computer networks showed a basic violation of the assumptions made by Jackson. In Jackson's work, we had assumed that all the queues are independent, but as Kleinrock discovered, and as we shall show very shortly, in computer networks, the packet lengths and the inter-arrival distributions are correlated, and also the same packet has to go through many different links, so the packet length does not change. And for a computer network, the service distribution, the service time is just the time it takes to transmit a packet, and that obviously is just a function of packet length, assuming constant capacity of transmission links. So he modeled the computer network as a connection of different queues, and he set up the model and he came up with an exact model. And he said that the average network delay a packet faces can be represented as capital T, and this is equal to the summation over I, lambda I over gamma multiplied by Ti, where lambda I is just the traffic on channel I in message per second. Gamma is the total network throughput. So we are assuming everything that comes in is output. So we can either take the total number of arrivals at all the different nodes, we can draw a cloud around the network and measure what amount of traffic is the outputted. So the difficult thing to estimate here is Ti, and this is essentially the same problem of estimating the response time of a queue in a queuing network. And Jackson's result did not apply because of the lack of independence. It was discovered that service time distribution is not exponential, and also the same packet must go through different routers, and therefore, because there is this dependence as well, because earlier we had thought that the same job does go to different queues, but at different queues the service demands are independent, but here we have this direct dependence on packet length. Also, the packet lengths on the internet are not exponentially distributed. Typically they are trimodal, in which you have peaks at around 40 bytes, around 500 bytes, and around 1500 bytes. So this does not look like an exponential distribution, and because of that the service times were also not exponential. A further challenge arose when you had multiple links connected to each other. So we have a figure shown. We see that even if the arrivals to the first queue are exponential, assuming that now router is carrying also other traffic and it is near the bottleneck or the maximum utilization, the output of this router would be more or less deterministic, and it is only a function of packet length. And for the other router, again the service time it would take at that router would also be a function of the packet length. So in effect, at the second queue, the dynamics of the queuing system is completely different from the dynamics of the queuing system at the first queue. This is because of the non-exponential service time distribution of the first queue and the dependence of packet length and inter-arrival times. We can also note that the inter-arrival times of two packets at the second queue must be greater than the transmission time of the second packet at the first queue, because the inter-arrival time cannot be less than the transmission time of the second packet. It has to be transmitted before it is received at the other end. Another thing that is noticed is that the long packets typically wait less at the second queue. To understand this, we can imagine that on a motorway there is a slow moving truck. And because it is a slow moving truck, while it takes a lot of time to transmit or go to the other end, but when it goes to the toll booth, it would almost always see an empty booth, because the booth has had plenty of time to do away with all the service demands. The earlier customers were not as slow as this long packet, and because of this, again, we have this dependence of the packet lengths and the service times, and because of that, things get complex and we cannot have tractable results. So the engineering solution Kleinrock came up with was simply to assume something that is patently false, but something that gives us good results. And this assumption was that every time a packet comes at a queue, a new length is calculated for it from some exponential distribution. So if we make this assumption, then we restore the independence, because the justification of this is that if you have a lot of traffic, then because there is a lot of multiplexing and different flows would have different length of packets, you tend to regain the independence. And if we have independent service centers, then this is exactly an open Jackson network, and we can analyze each router separately as an MM1 queue. And from that we can derive the relation for TI, which Kleinrock calculated, and it was a good approximation for the case where we have high amount of load, we have exponential arrivals, or if we make these approximations, then this Kleinrock independence assumption would give better results. But in general, if you have a lot of multiplexing and high load, this gave acceptable results. So this was a big breakthrough and marked the first event after the introduction in queuing theory and the first major result in analytical modeling of computer networks. So this then brings us to the end of this session. Let me now summarize the things we've stated. We've stated that queuing networks can be modeled and analytically solved, but only if they have a special friendly character. If they have a product form solution, then we can analytically solve them. But if they don't have this product form nature, then it is very difficult to analyze them and do anything about them in a mathematical fashion. Also, we've seen that queuing network models are useful for modeling computer networks, as shown by the work of Kleinrock, and a lot of work has been done to further extend the work done by Kleinrock. With this, I would like to conclude this session. I'll see you next time, inshallah. Assalamu alaikum wa rahmatullah.